Alright, we're going to look at some basic operations when we're in polar form. We've already looked at ones in component form, and some things are quite easy when you're in polar form. So if you've got vector v defined as 330, an example of a scalar multiplication is quite easy to see. So -2 being the real number on the front of the vector, a scalar of -2, well, basically in polar form the magnitude is always positive. So if you haven't noticed that, that will always be a positive quantity. It's the direction that will reverse its effect. So that will be a positive, and so if we've got -2 on the front, we multiply the existing magnitude by the absolute value of 2, -2, which is just 2, and we get 6. And then basically, if we look at the direction, that's the thing that is affected by the negative there. It flips it around 180 degrees. So you could add or subtract 180. Now, why haven't they added? If we added it, it'd be 210. And you might remember from a previous video, a lot of sources prefer to use what's called the principal argument and keeping theta between 180 negative and 180 positive degrees. Okay, but you can still add the 180 and you get 210, but sometimes that's not preferred. So if you're happy to keep it between negative and positive 180, we subtract the 180, so that flips it around, and we've got a geometric description over here. So we've got our vector v there and -2v there, and you can see the angles. So that's an easy one. Let's look at one that's a bit more sophisticated. In the past, we've looked at finding the sum of two geometric vectors or two vectors in component form, and we add the corresponding components. We just make sure that they're head to tail if they're geometric, and it's fairly straightforward, to cut a long story short. However, when we've got vectors in component form, polar form, it's not quite as straightforward. I'm going to show you two methods that do the same thing, and the first one's using the sine and the cosine rules. So using trig basically in the first one, and this might be something you see from a math methods perspective, but they won't do vectors in math methods. So in the diagram, we need to define u and v in terms of some position, central position O. So basically, if we've got u plus v, we need to add them together, and you can see they've got that there. They've got u equals OA, so there's u or OA there, and we've also got v, which is AB. Okay, so we've got that there, and they are head to tail, and we want to find the resultant. So if we're finding the sum of the two vectors, we're trying to find u plus v. So that would be OA to AB, and OA to A plus AB is OB. So that's the resultant. Alright, it's a non-right angled triangle, so we can't just use our regular trig ratios. If you've covered the cosine rule in Year 10, you can use that, and you've got your values there. We're trying to find OB, and that comes out as square root of 364 or 2 root 91, or perhaps a decimal approximation if that's okay for what you're doing. So we've got OB, and we need, see, that's the magnitude, isn't it? Because remember, we're finding a vector r comma theta form, so we found r essentially. Theta, we need to use the sine rule here. So you might remember the sine rule too from Year 10. Obviously, if you've not covered the cosine rule and the sine rule, you wouldn't be able to use this method. And we get an angle. The angle of the vector is called BOA on this diagram. Let's have a look at that. So BOA comes down here, BOA, and that will give us the angle of the vector. And basically we get 33.004 is the angle that separates these two vectors here. But that's not the answer. Remember, we need the basically from the I direction, okay, because we've got two-dimensional vectors here. So in the I direction, is where we start measuring. You might remember from introduction to polar form, 0 is a bit like with the unit circle. 0 is in line with the x-axis and theta goes anti-clockwise. So remember, that's the I-axis and that's the j. So we need to look at what it is in regards to the I. And it's another 30, isn't it? You can see the 30 there from earlier in the question, because the 30 was the vector OA. Okay, and if we go back there, that's where that 30 came from. So we need to add another 30 on, and we get theta is 63 degrees approximately. So that's one method, using sine and cosine and relating it back to the x-axis, which is the I direction. So the other way is, for those who are a little averse to that sort of trig, this way might appeal a bit more. This is going to do the same thing. Remember, the original two vectors were 10, 30 and 12, 90, and you can see here that 10, 30 and in both I and j form, because remember, you've got r cos theta, r sine theta. So r cos theta I plus r sine theta j. You may need to go back to one of our earlier videos if you've not seen that or you can't remember it, but that's the form. So that will give us u. Okay, so remember, r was 10 and theta was 30. There they are, right? So the next one will be the same for v involving 12 and 90. Now you might notice that it's just 12j there. V would be, r was 12, so it would be 12 cos 90 I plus 12 sine 90 j. Cos of 90 is 0. Alright, so that turns into 0 basically, and sine of 90 is 1. So you have all of this term here is 0, 0i plus 1 times 12, 12j, and so that's why it's j. These ones here, cos of 30 is root 3 on 2 times 10 is 5 root 3 I, and sine 30 is a half, so 10 times a half is 5j, and then you simply add them together, and so you've got corresponding components here. So we've got 5 root 3 plus 0 is 5 root 3 I. We have in the j's, we have 5 here and 12 there makes 17. Now you can leave it like that because it tends to be a bit nicer, but if you need to have it back in the original polar form, you need to reconvert it back. So remember, r is the x squared plus y squared, take the square root, and that's the same as the 2 root 91 from above there, yay. And theta is inverse tan of y on x, so inverse tan of 17 on 5 root 3, and just be careful, you might want to draw a diagram there just to make sure the 63 is the right angle, and we know from previously it is. There it is. Okay, but always, I recommend you always draw a little diagram just to make sure tan is spitting out the correct angle in the correct quadrant. Alright, so always draw a diagram, and there we go.